Okay, hello everyone. This is the additional video for chapter 13. Okay, so we will start with the vector valid function. So to begin with, we need to start with some definition. What is vector valid functions? So a vector valid functions is a functions whose domain is a set of real numbers and whose range is set of vectors. Now this is become important. Okay, so what we are doing here is actually we are dealing with the just a typical function, but the function is in vector space. Okay, vector space. So if this vector space we can simply write as this, okay? And it's denoted by RT. Okay, so we can describe RT as a vector, and let's say we have F and then G and H, and these three vectors, or these three F, G and H, are all component of the R. Okay, this is real valued functions, or we call also this as a component functions, or component of R. Okay. We can rewrite this in terms of basis factors with I, J, and K. Oh, sorry. So if you have meaning that this functions f is d cube, g is ln, and h will be square root of d. Okay, so basically all the things in our chapter 13 will be practically similar. The difference is just the output is vectors. Okay, now we start with limit and continuity to begin our calculus observations. Now if R we can write as F, G, and H. Then if we take the limit of this R, then we take the limit for all the component. Okay. And of course, this is provided the limit of component exists. Okay, so that's the first one. So nothing extraordinary or anything that's really strange. Okay. And continuous means that R is continue at some point A if the limit is equal to when we evaluating at exactly that point. Okay. Okay. Now, if we can trace the curve, okay, for this R, okay, Let me write in the new slides, and let's put on the graph. Okay. So let's observe the red arrow, the curve C. Okay. So if we can set the so suppose the F, G, H, they are all continuous real valued function on some interval I. Then set of C of all points x, y, z, where x is ft, y is gt, and z is ht, and t varies throughout the interval I. Then C is called the space curve. And the equation here that describe x, y, z will be called the parametric equations of C. And t is our parameter. And what's the implications? The implications means that we can describe, for example, if we have this R, we can take this in terms of x, in terms of y, each component of the R. And if you remember the equation of line, then we know that this is actually a line that passes through 1, 2, and -1. Okay, this is 1, or maybe using different color. 1, 2, and -1. Okay, that's the initial point or pass through point. Okay. And also the line is parallel to vector 1, 5, and 6. So 1, 5, and 6. Okay. We can also observe through the condition or the relation between R and R0, where R0 is 1 to -1, and our phi, the vector that is parallel, is 1, 5, and 6. So all the shape that we have discussed before, we can actually refer them into our vector valued functions. Okay. Now, if we have another vector, let's say we have cos ti plus sin tj plus tk. Okay, if we describe this in parametric, then this is for x, this is for y, and this is for z. Okay. Now, if we observe this x and y, we can observe that if we want to make it into our circle equations here, this is true, right? So this is true for all t, okay? So the curve, they must lie on the circular of the cylinder. Okay. So So if we try to make out the shape, then this is the most possible shape for our vector value functions. So we can start from, imagine when the z is 0. So imagine z is 0, we have a circle, perfectly circle on the plane, perfectly circle on the plane here. And then we take some z, for example, we start from 0 here, we consider some point, okay, and then take some another point, okay, pi over 2, we start from 0, and then pi over 2, and we take some other point as well, and I think we can take some t for some angle, okay, so like pi over 2 pi, and then 3 over 2 pi, and then 2 pi, and we are going to observe that the curve will be a helix. Of course, this helix, if you remember some class that you have in high school about biology, you will remember that in our body we have a double helix for our DNA. It has a helix that is parallel each other. It's called the double helix. Okay, another example. Find a vector function that represent curve of intersection of cylinder and plane y plus z equal 2. Okay. Now, to take this y plus z equal 2 and maybe describe in the picture, then you can start with y plus z equal 2 as a line, and then in the x-axis it will have some infinite value, and then it will be having a plane. So you can start with, if we imagine this, let me just take a small graph here just to imagine how it looks like for this y plus z equal 2. So y plus z, let's just take this z and y. So for example, we take z and y and make it into 2 and crossing this, right? That's our line. The plane means that we will have some certain plane that is fills out our y plus z equal 2 line, okay, and that's our line. And then imagine this, and then we have another one that is cylinder, in which we have a cylinder here, and let's take maybe around here. So imagine that we have a cylinder, and then using this plane to cut through. So using this to cut through, and maybe we can take more longer for the line here. Okay. Okay. So imagine you have a plane that is going to to cut through the cylinder. Okay, I think I have also prepared the picture. Now if you look here, that is passed through some ellipse. Okay. If we check, and try to use some numbers, we can take the we can write that the x, for example, is cos t, y is sin t. We can have our t described from 0 to 2 pi, and from y plus c equal to, we have c is 2 minus y, or 2 minus sin t. Okay. Now we have 3 components. So we will have a vector positions or vector equations for r, so first we can take t maybe from 0, and then pi over 2, and then 3 over 2 pi, and then 2 pi. Okay. And then look on how they perform in all this x, y, z, and then you will see that this is precisely what the numbers means. Okay. And similarly, okay, if you take another example, okay, you have a paraboloid. Okay. Find parametric equation for the curve intersection of paraboloid to the plane. So paraboloid is this, and plane is this. Okay, you can take this as example and try to write down the parametric equations from here. This is how it looks like. And that's the 13.1. Okay. Okay, now we are looking at the next sections on chapter 13, which is 13.2, the derivatives and integrals of vector functions. Okay, now before we look on this graph, maybe let me just write the derivatives. Okay. This is not much different than what we have in the definitions in calculus 1. Okay, still the same definitions. So if limit exists. So if we're looking at the geometric significance on how these definitions can be true, okay, if we start with a point P and Q, okay, they have this vector positions, and then they have this results, okay, the difference between the vector position rt plus h minus rt. Okay, and if we are looking at this one, okay, if you imagine this is our curves, that then the pq is our secant. Okay, so our secant factor. If you remember what we did last calculus 1, we have exactly the same way. Okay, and what we did is we are going to take this q, going to closer this p, or maybe from p also going to closer to q, and then this distance is going to be closer and closer, meaning going to be 0 at the very end. Okay, and now when we are imagine that the q going to move out to some point nearby this p, maybe here. Okay, if we describe this is the point that we want, then we describe the conditions here as our tangent, right? Remember the tangent. Okay, so we have a tangent here, in which we can describe as this, our tangent r prime. Okay. And then if we are going to take this if we are going to take these vectors and multiply with 1 over h. Okay. This 1 over h is just a scalar, so 1 over h is just a scalar. So that means the direction is still the same direction with the vector pq. Okay. So as the limit of this q, okay, so if we are going to take the limit, okay, so take the limit as h is going to be 0, then this will be equal to our derivatives. Okay. And the implications of what we did here is basically, if we have the vector of r, and f, g, and h differentiable, then our derivative for these vector valued functions is we take derivative for each one. I don't think we need to really prove this one. I think we can imagine from here, from this limit here, we take the limit of this, means that we take the limit of the f, okay? Like for example, f t plus h minus f t over h, and also for g, for h, and the implications is we will have this relations. Okay, another thing that essentials in chapter 13 is we have terms called the unit tangent vectors. This is described by this t. It's similar with what we have before in chapter 12, the unit vector, but this is for our tangent. So we have a terminology for our vector valued functions in calculus. We have a unit tangent vector. So tangent in terms of unit vector, okay? Let's take example. Let's say if we have the vector functions, find unit tangent vector at t equals 0. First, we can differentiate the r. Okay, and then we take this is just I for vector at t equals 0, and then we can take the derivative and input 0. This is j plus 2k. Okay. Now t0, this is become j plus 2k divided by 1 plus 4. So we will have 1 over square root 5 j, sorry, plus 2 square root 5k. Okay. Okay, let me go through next sections. We have some differentiation rule that probably you need to take some time here. So suppose u and v are differentiable vector functions. C is a scalar and f is a real valued function. Then all this derivatives formula will be we can apply this formula. So remember that the u and v is vector, differentiable vector functions, and c is a scalar and f is just an original real valued functions. And notice that we still have the product rule, right? And this is having similar with the product rule, but it's actually the dot, the cross product. But the dot and cross product, it's having similar pattern with the product rule. Okay. And the last one will be the chain rule. And then another theorem that is if the magnitude is a constant, then the derivative is orthogonal to the vector functions for all t. This is because from the dot product, this is a constant, right? And because it is a constant, if we derive then this will be, we can write, and we know that this will be 0 because it's a constant. We derive and become 0, right? And we say that the R prime is orthogonal to the vector function itself. Okay. Okay, now derivative is complete, and we can move on to integrations or integrals. We start with the our approach within the vector functions. Okay. The same definitions or similar definitions. So we start with the definite integrals. It's similar, except that the integrations that we have is a vector. This is a vector. And we can express R in terms of F, G, and H. Okay. So similarly, when we have this, we can describe this R and describe in terms of each factor or each component. Okay, or we can say that is equal to integrations Okay, now this is the first one for integrations. And yeah, okay, you can pause the video if you want to take some notes, and I will just keep going a little bit. Okay, you can also write the factor, the integrations as antiderivative, where R is antiderivative of R, that is R prime is R t. And then we can also just write RT dt for indefinite integral. Okay, so mostly chapter 13 is based on that, and there are some additional one that I will explore later in the class. We have arc length and the curvature, so we will move on to that sections in the class, and also having some more exercise and practice for chapter 13, and then we finish, and then we can move on to chapter 14. Okay, so that's it for 13.1 and 13.2.